I forgot to raise the desk, so let me make a little noise here. It's just sort of weird. So we're at the home stretch. Can you believe it? It's our last day of lecture. Tomorrow we'll do a final review. And then what I had originally on the calendar was that Monday was going to be a makeup day if the university had to cancel a day for raining or whatever, or if we were just terribly behind, neither of which happened. In fact, I'm really happy with how far we've made it. We made it through the entire textbook. I can't remember the last time I made it through every single chapter. I always make it through where I must, but rarely make it through where I dream. So we've gotten a lot of stuff done, and that's far more common with summer classes than semester classes anyway, because I'm not exactly sure why, but I think part of it has to do with the fact that we don't splice it, chop it up into such small pieces, and that ends up burning up ramp-up time in the beginning of each lecture. So thumbs up to you guys for making it, and we still need a homework, and there's one due tonight because you guys asked for an extension. So you're going to get homework number 9, and then 10 we'll do together probably in the second half of tomorrow, and it'll count as part of the homework. It'll count as a homework, but it'll also count probably part review for us. So I've got to figure out exactly how I want to approach it. But you definitely want to tune in to tomorrow's lecture. Okay, so today we have the last 2 sections of Chapter 9, and this one's really going to talk about what approaches we have to try and build networks that can actually support different classes of service. It comes up in the multimedia networking chapter because multimedia is one of the most common intolerant classes of traffic when it comes to dealing with variances in delay, such as jitter or overall latency from one end of a network to another. So, and it's understandable. So we can use that as a decent example and kind of walk our way through. So we may not need 2 hours to do this, and so I also have some fun things like a project called the Distant Early Warning Network, which is a series of subarctic network terminals that were built for the United States government, and we'll look at some of that, which is kind of a bizarre network to build. And if I can strike gold and find a couple of the images of the antennas that they had to build, it's a weird, different type of wireless network than we've looked at, and I don't know if they're even still being used or not. I think they've been largely decommissioned. Okay, so I think we'll have time for that as well. All right, we've gone through looking at what the multimedia apps are. We took a long look at how to stream stored video, and I think you'll agree it's an easier way of transmitting information. Users may be impatient to see the data, but at least you can, buffer and pre-process lots of versions of your file ahead of time, so you have one that's suitable for different transmission rates. So even on an existing connection, if the user is not moving around or something, if the bandwidth available to them on a somewhat congested network changes over time during the course of the movie, you can change the size of packets that you send, but normally you can just buffer some. And not that long ago, we would download the entire movie first before we played it. In fact, when you bring a DVD home, that's exactly what you're doing. The other type of transmission, which is more difficult, is trying to send video real time. And I'm a little surprised they didn't sort of break out a separate section on that. They sort of lumped some of that into the conversational applications discussion. But real-time video is more of interest to users in being broadcast as it happens, particularly if it's something where people want to stay in sync with each other, like stock market video or sports games and things like that. But we spent a lot of time looking at a fair bit of science that exists around measuring how well you're doing. And we looked at one acronym in particular, MOS, and it measures people's score, the objective value that they give to how good this thing sounds. How well am I able to understand what's going on? So we've worked our way up to finally looking at what the network can do. Most of these other things were things that you would do inside your applications when you didn't really have all the control that you wanted. So it's time to look at what we can do in the network. One big approach is just to do the best you can with the bandwidth you've got. And what I just talked about assumes that that's what you have. If you find that you don't have less bandwidth, then send less. There's nothing else you can do about it. Or decide to wait a little bit. So that's a best efforts network, and that's generally what we're willing to do. If we're willing to sort of just throw money at the network and make the bandwidth bigger and make the routers faster, then we really don't need any more refinement than that. If the roads are always big enough to handle rush hour, then you don't need to worry about restricting certain license plates on certain days or setting up HOV lanes or not letting people drive more than a certain number of miles a year or charging a toll. You don't have to do any of that stuff. If there's plentiful resources, then you just let things happen best they can. And that's a decent approach. We've done a lot of that because it's simple. And as long as it fits within the business model of the ISP, then you can do that. Yay, we have a customer. So I've been here by myself for the first 10 minutes. So, well, not really, because you guys are out there. Welcome along. So this is, I'm not sure if this is less awkward or more awkward. there's just one. Yeah, maybe a little combination of both. Okay, so we're talking about the brute force way of throwing bandwidth at it. And when I worked at AT&T, that was a popular answer. Just IBM, install bigger network. If you install more bandwidth, you can get more things done. So there's typically no guarantee of service. The problem with this approach is you don't usually have control over the whole network. You usually only have control over the first leg from you to the ISP. Come in. Hi, come on in. There'll be more people coming in. There are some line as well. Welcome guests, guys, and I won't put him on the spot by introduce himself and stuff, but this class is hybrid, so some people are online and some people aren't, and a lot of people watch it afterwards. So it's a decent-sized class, but only a few people come for the live part every day. So you're welcome to stay as long as you like, and just tell me how long you want me to tell her you stayed, and I'll be sure and do that. So the problem with this is we usually only have control up to the first leg, up to the first router. So you'll have institutional control, and you may have control up to your ISP. So if this is your ISP over here, and this is your carrier, you can buy bigger bandwidth. So this is what somebody's going to show up and try to sell you. This is your own dedicated link. So this would be your frame relay circuit, or your Ethernet circuit, or your Sonnet fiber pair, whatever it might be. This typically is going to be inside your organization, and sometimes this can be a wide area network as well if you're in one city and you're tunneling back to another one. But generally speaking, this is a LAN for most of the time. So someone will come up and show you this, but no one will ever come and try to sell you a bigger one of these. What they'll try to sell you is more service. So they may give you 10 megabits per second, 50 megabits per second. They may sell you a chunk of bandwidth, but they're not really provisioning maybe a circuit directly for you. Typically what ISPs will do is they will charge you based on how much traffic they need to be able to send down the pipe that you bought between you and them. So if you want an Ethernet connection to the internet, you find an ISP that you're happy with, that's got enough bandwidth out to other sites, maybe to tier 1 ISPs or to NAPs or things like that, and then you carve out bandwidth. You usually won't run a dedicated circuit straight to them. As we've talked about all semester, you'll usually buy something on a packet switch network like frame relay or MPLS or Ethernet, and then you'll provision a PVC, a private virtual circuit, just a logical path, and reserve some of your bandwidth on your end, and then they're going to have to obligate some of their bandwidth on their end. So you both have to have pipes physically big enough to get to the carrier's cloud in your city, and then the carrier is going to have to have enough bandwidth between these two nodes to allow you end-to-end to provision what you want. So if you decide out of your 100 megabit per second circuit, you want to provision 10 megabits or reserve, as we might also say 10 megabits per second for internet traffic, then you will have to get together and both sides have to sign off. You can sometimes do this online. Usually a person's involved and tack up a 10 megabit per second circuit. That doesn't guarantee you're going to get 10 megabits worth of streaming bandwidth out to the other side. From here on, it's still best efforts. So this solution isn't sufficient. It'll get you good bandwidth to the cloud, or at least to the first hop, but it doesn't guarantee anything past that. So I sat in a meeting with a totally ticked off customer from France, and I can still remember I can see myself in the meeting now. He was super furious, and I was with a salesperson, and this guy was upset because they had bought an internet circuit from us in Houston to go to their main office out on Katy Freeway. It was an oil company, and they knew very well in Paris the path that they had and the type of circuit they had to their ISP over there. And we could trace route between the two and look at other types of network data, and we could see that there was a very fast, low latency direct path between the network access center in Houston, the Internet Exchange Center, and one in Paris. There was a big circuit that ran pretty much straight there. And yet when they ran traffic over this thing, they didn't really experience that latency. And they wanted us to change the way we were routing things. Well, the problem was that they were trying to use this as a private circuit. They wanted a guarantee of bandwidth, and they wanted a guarantee that they'd only have a certain amount of delay from one end to the other. And I was on their side. I was trying to fight their battle. So I got into a big fight with the guys that were provisioning the ISP in the background because I was trying to champion things for my customer, but we did not prevail. We did not win that battle. And what the company wanted them to do was basically, if you want an international long-distance private line circuit, then buy one. Well, so what they did was they just bought internet service from somebody else. So we lost everything instead of keeping this and trying to tune it. And it made no sense because it was pretty clear to me that these guys were intentionally refusing to route things in the most efficient fashion just to steer business one way or the other, which violated just some fundamental philosophies I have of send traffic as short a distance as possible and get it off the network as soon as you can. And they weren't of the same page. So best efforts is just the first step you can have. If you want to try and do something more, one of the things you can do is try and identify the traffic that ought to be treated differently. And this, in general, is referred to as differentiated service or prioritization. And way back in the beginning when IPv4, when we looked at it back in chapter 4, maybe 2 even, when we looked at the type of service field, we sort of brushed past it because it's been changed, its use has been changed over the years. But even predecessors to IPv4 used this type of service field with this in mind. What they were trying to do was give people a way to mark packets that they wanted to have given a different type of priority. So there's pros and cons for this, and as we get through this, I'll mention some more attributes of this and what parts of this improves and what parts of it still doesn't address. You still don't really get a guarantee, but at least you now have a class of traffic that you can have. And we have other ways of handling important traffic differently. You might, for example, unbeknownst to the user, prioritize traffic that's sharing link state information between routers. So as links go up and down, people know about it sooner. And this idea basically is to mark packets. So you either set a bit in a header or you teach the router to look for certain port numbers that are typically used for traffic that generally needs better class, like the port number that Skype uses or the port number that WebEx uses, for example. You also can do things called scheduling, where you will spend a certain percentage of the time pulling packets out of the queue that this higher priority traffic is in, and maybe a smaller percentage of the time you pull traffic from the other queues. So this would be like pulling up to a toll booth and there's multiple lanes and somebody says, Or better yet, if you've been to the airport and you've seen the first class or TSA line, they'll pull somebody from there if there's someone, and then maybe somebody from one of the other lines. And then they'll go back and pull somebody else from there, and then maybe from one of the other lines. So they get through faster, but the other group, and this is really, really critical, the other groups don't get starved. So one of the big risks with differentiated service is that you set up some simple, overly simple rule that says, I'm always going to pick priority 1 first. And what happens if priority 1 is sending you enough traffic to fill the buffer and to fill the link? Then what happens? You never get to the other traffic. So this is a risk with router management as well. The other problem with differentiated service is there's no guarantee that the next router or the next one or the next one is going to play along. And the big challenge with the internet is the path is owned by lots of different people along the way, and there's usually many different managers of the routers. So this is sometimes helpful if people just happen to agree that they're going to give prioritization. They're going to bother looking at the prioritization field and paying attention to it and respecting it. But respect is even a little bit strong because there's no obligation to do it. It's not like they're doing something wrong by ignoring it. They're just doing something nice if they don't. And you have policing in here as well, which if people figure out all they have to do is mark packets, then guess what happens? All right, so this one's a little bit tougher to deploy, and it's used widely inside of organizations. This is, as I've mentioned before, this is how I'm convinced my WebEx traffic gets through a totally oversaturated campus network at the other University of Mexico where I work, and yet still makes it out to the outside world. My recordings somehow manage to still be intact, and the audio and video are pretty much intelligible. Well, at least as intelligible as I am. Let's put it that way. And this basically does things in buckets, in big classes. So you will throw all streaming audio into the same bucket and all streaming video into the same bucket. Well, if you're teaching a class using video, maybe you want to give that a higher priority than YouTube. They're both streaming video, and maybe you don't want to give both of them the same class. So there's a third category that you can use, which is called per connection quality of service, where you design a more rigid set of rules to identify which traffic needs to get higher prioritization. And this you manage on a per connection flow. So between an individual sender and an individual recipient. And remember, connections aren't just on a per machine basis. One computer can have many, many connections at the same time. So this is very granular. And you can even become more granular than this and pick out certain packets from within a stream. So for example, if you're sending a WebEx broadcast and they just happen to mix in audio, video, and slide updates into the same stream, then maybe you need to get a lot more sophisticated. But generally, you're asking for big trouble if you try to do that, because no one's going to go to the trouble to pick things apart. So you should put each of those parts of your communication into a separate flow. So if we used Wireshark and we pulled WebEx data, one of the things you might find is that audio and video and whiteboard are on separate TCP strings. You might, or one of them might not even be on TCP. So this is has the ability of improving and their ability to perform or provide guarantees. So this is where large ISPs, nationwide backbone providers, have an advantage, because if you are trying to deploy such a network and you don't necessarily want to buy private line service, they can offer you a hybridized service because they usually have a point of presence in most major cities. So you can get most of the way there knowing that the manager for all of the routers along the way is the same firm, and they're going to use the same rules, and they'll provide the same policies to you. So is that internet? Well, I mean, that's sort of like asking, is Netflix internet? It's a content delivery overlay network. You can argue that one way or the other. But if for the purposes of multimedia, what we're just trying to do is figure out what kind of mechanisms or tools can we get our hands on to actually implement this type of prioritization. So once a flow is admitted to the network, it's marked, you add rules to the Router, typically you don't just depend on, you don't just trust the user's markings of packets. Usually teach the router about things, and you can get good default packages and lists that say, okay, here's generally the ones that hurt the most if they're not given prioritization. So if you just want to do a rough pass at it, I suggest you set up these 5 queues, these 5 buffers. You distribute your weights this way, 20% for this, 15% of the time you pull them out of this, etc. You refuse packets bigger than a certain size in these flows, and you allocate this much buffer memory to each of them, and you route traffic with these port numbers or these destinations, and they'll just automatically give you a default to go by. You don't have to start with a blank sheet of paper. And that's valuable. That's usually a really good way of doing it. It's just sort of like saying, you know, by default, you should paint your emergency vehicles red, and you should teach them to drive in the left lane. And, you know, there's lots of other red cars that drive in the left lane, but that's generally a pretty good rule to do it. So you've got packet marking, not market. You have scheduling, you have policing, and then this last one of call admission. This is something the internet generally does not do, but you can find parallels to it. This is something where before you initiate transmission, before you start sending a voice stream, you have some protocol, some management addition running on your routers end to end that allows you to ask them, hey, I need to set up a phone call. It's going to be 6 kilobytes per second. Can you set up will you agree to put this in your priority 1 queue? Yes or no? And you can ask the devices along the way. You can get far more strict than that, like the telephone network, and you can say, thou shalt reserve a channel of 64 KB per second between this port and this port, and leave it there until I tell you to tear it down. And it's like, yes, sir. And so that's a dedicated, nailed-up bandwidth channel that you can use for something that's constant bandwidth. But that's not shared, and so it's inefficient. Remember the example we gave yesterday where if somebody sets the phone down to go get a recipe, the phone network still is reserving all that bandwidth, even though you and I was like, why are we wasting packets on this? Nothing important is happening. So call admission is a way of setting up some preparation before you allow the person to initiate the communication. These are the most complex ones, but they're also by far the most valuable to a firm. So if you end up in network management, you're going to end up being asked to manage and deploy these types of schemes. So particularly in a very congested area, like Telmex has the largest cellular network in Latin America, but it is just, at least in Mexico, totally oversaturated all the time. It is a huge quality of service issue. So one of the things that they should be doing is looking for ways of generating more revenue that by offering people higher classes of service that would not only give them a user vote in whose traffic should be prioritized because they're paying more. Okay, so clearly they're willing to pay more to do it, and it gives them more revenue to upgrade their network. So there's a business model in there that everyone would be happy with. So one of the things this doesn't talk about in here that's a huge political issue is net neutrality. And you guys have heard of that, I assume. Yep. So you have to kind of have your ears closed this year to not hear about it. So net neutrality is this philosophy that all traffic that shows up at your doorstep of your network should be handled equally. So if the buffers are getting full and you have to drop packets, you drop them in a egalitarian, non-discriminatory fashion. You just don't gang up on one type of user. Even if it looks to you like this one class of user is the reason why your buffers are getting full. And if it wasn't for them using a bunch of the bandwidth, everybody else would be fine. So why not drop the person that's causing the problems? That's sort of the idea. So this would be like, and the people that don't like this idea, saying like, well, let's say you have a house full of refugees from Hurricane Harvey, and you only have enough food really to feed 10 people, and an 11th person shows up. Do you starve them, or do you divide things up and everybody doesn't get to eat as much as they wanted by 1/10? so that there's enough for, or roughly that, so there's enough for the others. So as you can see, when you start aligning things to money, politics, or religion, the emotion gets pretty high. You start aligning it to starvation and feeding, and we actually use some of these terms in networking. So the rule that came down from the United States government's agency responsible for policing this, the Federal Communications Commission, was up until last year, time flies, I think it was last year, that you need to treat all traffic equally. It needs to all be equal. So I can see both sides. I could argue vehemently on both sides of this issue. I've been all over it and all around it for years and years and years. And this was a big discussion, and we used to have internal debates to figure out sort of what we thought was fair. The pragmatic side of this thing is if you're a network provider and you get no revenue from people showing up to your network, in other words, the way the internet was sort of built is everybody pays kind of a flat rate as a user, and they all can use the internet. This is like you pay for a license or a license plate on your car. You pay your annual registration. You can drive as much as you want. Except we don't really do that. It doesn't work that way. We do charge people more the heavier their car is or the bigger the vehicle is. And if it's a truck, it pays thousands and thousands and thousands of dollars a year because they wear the roads out faster or they use more capacity, as we might say. So this model where everybody kind of pays a flat rate allows people to pull off whatever they need, and the phone company has models built that basically say, all right, on average, this person's never going to use across the year, they have a gigabit connection, but they're never going to use more than a meg per second on average. In fact, on average, you can combine many thousands, if not tens of thousands of users on a connection that is as big as any one of them's been offered, and you'll be fine. You can still do it that way. So for DSL that we looked at, where you have maybe 4 to 6 megabits per second per customer, you can put 3,000 to 10,000 users on one circuit that's that big and handle all of their traffic. Why? Because of two things. It's so fast that anything they get will only take a moment, so they're off of it. So the chances that they're on the network are very, very low. So that probability helps you when you're trying to figure out if you can combine lots of users. And the fact that this is still relatively large bandwidth, so you can get a lot of things done and people don't need it. The problem is when users start consuming a service that's paid you nothing, they're out on the internet somewhere, and they start pushing tons of bandwidth into your cloud, and these users start pushing this average way, way up, this collapses in the middle. And you get, let me back up a sentence, and you get no revenue whatsoever from them. So these are people showing up. So the other side of the argument says, you know, if these users are pulling bandwidth down, you should have factored that into your model. So you guessed wrong. So why is that my fault? You thought that you would be able to handle all the traffic these people wanted to pull down from the internet with this size of a connection. You chose poorly. Remember that scene in Raiders of the Lost Ark where the guy tries to pick the golden cup that Jesus had drank from, and the knights of the realm are there, the Templar are there guarding it, and he chooses the wrong cup and turns into dust and blows away, and then, you know, it's like this horrific scene, and they turn to this guy with the long beard, and he goes, "He chose poorly." So we use this phrase sometimes in networking when we're trying to make fun of people who make spectacularly stupid decisions and like collapse the entire network, and just as a jab back at them, like the time when MCI downloaded a patch to all of their Cisco routers across the country and brought their entire network down for like half a day. We were like, "You chose poorly." So there's a lot of passive aggressive sarcasm and networking, and it's a very important survival tactic. And nerds love this stuff anyway, so I know you guys will just eat this stuff up. You're taking notes somewhere in the back. You will be using this joke at some point soon. All right, so because that's how I did. So you've got this problem on both sides of things. What happened in the last year under the current administration was we got somebody who came in and just declared, we're just going to get rid of this net neutrality. We don't need it anymore. And so the problem, you know, this doesn't make carriers or the community This doesn't delight them. It might make them happy for a minute that they get a little bit of relief. But the problem is the way the decision was made, which was made with no input whatsoever. There were no hearings for this. It was made by somebody who just showed up and decided they knew best. And that's the rule that they made. That's like a dictator or something. And so that's a concern, because what we need these regulatory bodies to be is as deliberate and thoughtful as possible, getting input from as many areas so they can understand the problem as best as possible in the time allotted, and then make a judicious decision that takes everyone's needs into account, instead of getting elected or getting put in this position, having your ear filled with maybe one side of the story. That's risky. You may turn out to regret it. And what you don't want in regulation is people changing their mind, going back and forth and back, because it eliminates any predictability. And if you want to attract investment by carriers and others into improving infrastructure, you need it to be a stable, predictive environment. You wouldn't want to build an oil refinery right now in Mexico, because the presidential candidate that is likely to win, if you believe the polls, and boy, are those dangerous, is talking about renationalizing the oil company again, like they did in 1939. So people that have built assets from outside of Mexico, when they liberalized this a few years ago, they're nervous. And we've seen this happen. Venezuela basically took ownership of billions of dollars worth of American oil company assets. So what do you think the chances are somebody's going to go drop money over there right now? It's unstable. They're not confident that the rules are they're going to be able to hold on to their assets, that they're not going to lose everything. So this is bad when you're trying to improve network infrastructure, to have some fear that decisions are going to not be made the way they've been made before. I'm not talking about the outcome. I'm talking about the process you go through to make the decisions. I couldn't care less which way these things go, because I don't know as much as I should to make the decision, but neither did they. So I'm not happy with that. So it's a risk to the improvement of the infrastructure that we need to continue to grow the economy. All right, so we'll spend a little bit more on a few slides in here to kind of go over some of this stuff. We kind of reviewed everything we're going to talk about in the first few slides. So the approach of dimensioning networks. So this is one of the approaches. You're basically going to try and size or scale networks over which the only control you have is just to do as good as you can. This is the approach of just expanding the freeway, adding more lanes to the freeway, not trying to change policy or go around to businesses and try and ask them, as we did in Houston at one point 20 years ago, maybe 25 years ago. We went around as a society amongst ourselves and asked large businesses to institute things like 980s. Do you guys know what these are? In 9 days, you get 80 hours worth of work out of your employee. You get them to add time to every day for 1 week, and then for 4 days of the next week, that adds up to 9. And then they get the 10th day off. And then don't give everybody the same 10th day off. So you reduce by 10% the amount of traffic on the road, just from that, for those businesses. And you also implement telecommuting. Let people work some part of the time from home. And you invest in a high-speed line, and so the phone companies spent a bunch of money to put DSL around, and the cable companies spent a bunch of money, and wireless companies did what they could. So that's different than best effort. That's sort of changing the way people are going to use it. But what we usually do is we just add more capacity. That's typically what we do. When your hard drive gets full, do you really spend the time to go through and super categorize what's there and decide to push things off and look for duplicates of all of your files and decide to cut the cord on last year's PDFs and throw them out? Or do you just go buy a bigger hard drive? I mean, come on, right? So and when you run out of space on Dropbox, do you just blow it off, or somebody's actually started to pay a couple of bucks a month? So the approach is to just deploy enough capacity. It's very low effort, it's very low complexity. The carriers love you for this, but it drives up bandwidth cost. Fortunately, it's gotten unbelievably less expensive. So here's another one of those graphs. I told you sometimes they'd be inverted. This is what's happened to bandwidth costs over the last 30 years. When we first deployed a DSL line in a commercial trial in Austin, it was about $1,300 a month for a 4 megabit per second connection. And you can get it for like 10, I think, something crazy like that. So the challenges here are how much bandwidth is enough, and then how do you estimate what traffic demand is going to be? So the first modern time since the commercialization, the broad commercialization of the internet happened, that the internet was crushed and basically collapsed under traffic, was a day I can still remember. It was the year that Victoria's Secret decided to simulcast their show on the internet, and so many people, presumably males, watched that broadcast that it collapsed. That was the first time that our estimate turned out to be completely wrong. Now, we'd crashed the internet a bunch of times before then, but it was what I would consider to be generally pre-commercialization days, before it sort of made the water cooler news. It was just like a research interest. Okay, so that's one way to do it. The other way that we talked about was providing multiple classes of service. So best effort is sort of one size fits all, and that's generally what the internet does. The alternative is to partition traffic into classes. So this would be like VIP service. Everybody's used to going to the airport and seeing first-class passengers have their own line. We use that example pretty well. But the granularity is at a high level. This, again, if you remember, we're just looking at classes of service, not at individual streams. So this might cause you to give higher priority to all video streaming traffic, but it wouldn't give higher priority to WebEx versus YouTube, or Vimeo versus YouTube, for example. So this is helpful, but what mathematicians might call necessary but not sufficient. You need more to be able to do this. And we talked about mechanisms for doing this. MPLS had tags that isolated IP addresses down inside the datagram, and we basically had separate ways of marking things. You also have the TOS bits from history that are still a field in the IPv4 header, but not too many people pay attention to those. So the idea for classes of service is, again, remember the purpose of this section of the book. We're talking about things you do in the network now. For the previous sections of this chapter, all we had talked about were things that you would do as an application developer inside your host, inside your server or PC. Now we're talking about the things that you can do inside the network. So in this case, you might set aside a separate queue for a certain type of traffic, and traffic from H1 to H3 gets prioritization first, and maybe the red stuff doesn't. So that's kind of an idea. You can have, for example, mixed voice and HTTP traffic, and HTTP bursts can congest the router and cause audio loss. So this is the problem that you decide you want to solve. So you can give priority to the audio over HTTP if you want to do that. Let me make sure I'm not missing. Okay, keeping an eye on the time so we can break. And then the principle behind this basically is you find some way of distinguishing packets one from another so that you can put them into classes. And you usually don't trust the user to do it themselves. You usually will teach the router how to spot it. So the router might be told rules that say any traffic coming from the CEO's computer, priority. Or any traffic coming from the Oracle financial system is probably handling live transactions from our e-commerce site. Give that prioritization. Or traffic that's carrying a certain type of video stream that is used by our video conferencing system, give that prioritization as well. You can go deeper than that, though, as we talked about with quality of service, and very often you'll see the O written as a lowercase letter. And this is needed if you find that categorization by itself is not enough. Sometimes it is. But what if a VoIP traffic, either maliciously or because there's an error in the code, starts to send traffic at a higher rate and fills the buffer all on its own? It just saturates the network and it generates enough traffic to completely fill this link. Then this is the starvation problem. Then what do? You just don't let any of this traffic get through. So one of the principles that we want to have is mark the packets so we can tell which ones they are. And the second principle is to isolate one class from another so one doesn't swamp or beat up on or starve the other one to death. And we talked back when we looked at routing protocols, we talked at a few different ways of doing that. Do you remember any of them by any chance? I hate to put you on the spot, but you're my choice. Do you remember the schemes we talked about where you make sure you don't just take everything from just one queue? It's a kid's phrase, round robin. Yeah, it's like some game. I don't exactly remember the games I played to use that because we played with dinosaurs when I was little. Anyway, round robin is one of them, and that's one where you just pick one from here and then here, then here, then here, then here, then here. And the way that turns out to give prioritization is you put traffic from fewer flows into one of these than you do the other. So if 8/10 of your traffic is going into here, that's low priority, and 2/10 of the traffic is going into here, just simply going round robin will get these users out of the queue faster. You don't have to do anything more sophisticated than that. Another way of going about this, if you guys remember, was called, Yeah, exactly. FIFO is another type of queuing. All those, that LIFO, FIFO, LILO, WeMo, WeWork. Okay, I'm making stuff up now. Another one, though, is weighted fair queuing, WFQ. And so this is one where you take your bandwidth and you allocate it, not round robin, but you say 15% of my bandwidth I will allocate to this, 20% here, 40% here, and so on. And usually these schemes are sophisticated because you'll usually put the internet traffic down at the bottom. And what you don't want to do is reserve bandwidth up here that is reserved whether it's used or not. You want a system that's sophisticated enough that if at any given time these guys don't need all this bandwidth, you push this wall up higher. And as soon as something shows up, you throttle it back down to a minimum, to a guaranteed level, and you get the traffic through. And in the systems that we used to design, we actually had 3 classes typically was usually enough to get things done. You had constant bit rate, and you had, what was the ABR? I want to say average bit rate, and then you had best efforts down at the bottom. So if somebody showed up and their traffic qualified to be put into this queue, you would guarantee that particular stream a certain amount of bandwidth, but it fills up. So what this means is it's dedicated to this class of users, but each stream eats a piece of it. And so the problem here is if there's only enough here for like 8 phone calls at a time, and if there's 7 phone calls and other people get to use it, if there's no phone calls, other people get to use all of it. But what happens if there's 9 phone calls and there's only room here for 8? The 9th call gets blocked. Or you can decide to put it in a secondary queue that competes with this one in a sort of a round-robin fashion. And they may have jitter, they may have issues, but at least you didn't block their call. Another thing you can do is if you find these 8 calls aren't enough, you just switch to a different codec and you compress their audio streams further. And that requires cooperation outside the router from the call manager, but this is why buying the call manager and the router infrastructure from the same provider sometimes gives you the ability to do it. You can go back to this user or to the call manager and say, stop sending me these 8 calls at 12 KB per second. Send them less. And it'll drop them to 10. And now you've just carved out enough room for another call. So people's MOS score is going to go down a little bit, but usually they won't notice it. Usually they can mitigate it. They switch to a headset. They turn up the volume. They close their office door. They shut off the fan. They move closer. I mean, there's things they can do to mitigate it in human factors, engineering. So 3 is often what ended up happening. And this was sort of internal internet traffic, IP traffic, and this is stuff leaving to go to the internet, typically. So your branch offices that were VPNing in they would end up in, you know, in this queue, for example. There we go. I can't circle it. Okay, and then principle 3, you want to use these resources as efficiently as possible, but that's just what we talked about. If somebody's got fixed bandwidth and they're not using it, reallocate it on the fly that instant to someone else. So this is why sometimes even at school with tons of internet bandwidth, you may find that your videos work better some days than others, or on a cellular network, because this stuff is all being done in real time. So this is a huge area of work. It's largely automated, and it's driven a lot by policy. So what you've heard me weave into this conversation throughout is decisions that you have to make. Like, what should I do if a night call shows up? Should I let it happen? Should I throttle other people back and risk them noticing or being upset? What happens if the person's using a package for software encoding that can't handle 10 KB per second? Can my call manager let them send it at 30K and then it will downsample it? So I'll give you an example of what's called rate adaptation. And this happens all the time. And I got to figure out if I want to give you a conference bridge example or a web. I'll do WebEx because you guys are familiar enough with that now. So I'm sending traffic to the WebEx server, and let's say I'm using 30 KB per second for my video, and I'm using 8 KB per second for my audio, and I don't know, 12 KB per second for everything else, including the drawing that I'm doing here. So maybe let's make it even worse. Let's say I'm using 130 KB per second for HD video, which it will support because I have a fast enough connection. I'm plugged in, let's say, to Ethernet. It gets up to this conference bridge. My traffic makes it all the way up here by miracle. Right? So I'm so far so good. And then all of you are out here on different speeds connections. So somebody here is on LTE. Somebody here is on Wi-Fi, but they're at Starbucks. Somebody here is on Wi-Fi at home, and somebody else is here at Wi-Fi at the Student Center. And what's happening at the Student Center right now? It's getting busier and busier and busier as the morning goes on. I know because I'm there every morning at the minute they open the door. And so first thing you see are a flood of strung out, completely tired, didn't get but an hour of sleep students who are here for Cougar Camp with their suitcases dragging in, and I'm like, oh, you poor guys, right? So they're going upstairs to get breakfast, but they're all getting on their phones and things like that. In fact, it starts before the doors open because they're sitting on the steps using it. And then more people start showing up. So this person's bandwidth is going to do this. Then you have somebody at home. Their bandwidth should be rock solid all the time. In fact, it may go up a little bit if somebody else leaves or whatever. But they may have some variability because they're, let's say, on a cable network or on a telephone network that takes some hops to get here. If you're generally at Starbucks, if you're there for this class from 8 to 10 a.m., generally your experience is going to go like that. Because people come in for their morning coffee, they hang around, but then it's time to get to work. And then you have a few people that hang out all day long, but I think it's less likely that they're there to actually do stuff because Starbucks said it was okay to come and camp out now, right? So, and then you have LTE users, and their experience is, it's like this. Depending on the cellular tower you're passing, and are you able to maintain LTE all the time? Do you get knocked down to 4G? If you do, is it ever going to go back up again to LTE without you having to turn it off and back on again? These are like, why are dogs' noses wet? These are questions I ask myself all the time. So there's a big issue for the software running inside of here, and for the coder-decoder, or known as codecs in general. And it's usually written all uppercase. And that is, what do I do to this signal? What do I do to these streams to push them down for each of these users? We learned yesterday about application-level commands that you can make to survey and find out how the buffer's doing, how to change rates and stuff. But this is that problem on steroids, because this is for each user having to custom fit what's going on. So one of the things the software can do is buffer more. And it's not, if you've ever listened to WebEx while hearing me live talk, you notice there's a delay. And surprises me that it's never a lot, many times more than it is, given what I know about the path that it's having to take to get to some remote place. So for us, this is probably in Dallas, in Richardson, Texas. So this is computationally very, very intensive. So when you design one of these codecs, you need to pick codecs that are very easy to downscale. So for example, if you decide to design your video packet where you pick first thing you put into the packet in your encoded version of this video frame are big blocks on the video picture. Like you took your video frame, let me erase some of this junk. Let me erase all of this junk. Let's say this is your your screen on your laptop or your television, and this is your video screen. If the first thing you do is divide it up into 16 big squares and take an average value for the color and brightness in this, and you mark that down, and then you do it here and here, and you continue on, it doesn't take very much bandwidth to encode this, right? So if that's the first thing you put in your packet when it arrives, and then the next thing you put in your packet is the detail that doesn't duplicate the data, you're careful not to do that, because you don't want to have to encode this thing repeatedly, but you find a way to add more detail to it, and so you use more bandwidth and you give a little more detail here that improves upon the rough image you had here, and then you do it again and you start filling in more detail here, and you're very careful in your research about how you do this, and the packet arrives up at the bridge and you find that someone's got all the same bandwidth you do. You just forward the whole video frame to them, no problem. But what are you going to do if somebody's got, not as much bandwidth? You can't send them the whole video frame. They're not going to do it. One thing you can do is lose this part over here. And that's very easy to extract from the video frame because you've set your data structure up to where there's some of the detail that you can start from this point and go to the end of the packet and just eliminate it, shorten immediately the size of the packet, and you never had to pick through or, God forbid, re-encode the video, like rebuild it in memory and then go with another codec and sample it differently to come up with a more compressed version. You don't want to have to do that. That's very often done. But a better codec design would be one where you've set up the data structure where you've incrementally built detail with the bandwidth in mind. You don't have to do this for DVDs. You don't have to do it for CDs or radio or television because you can count on constant bandwidth all the time. But if you're designing something for this type of scheme, a better design would be to come up with a packet where you can whack that stuff off. And then, what's this going to end up looking like if you decide you're only going to get this? Well, you see my picture on the screen here, right? It's going to look like that. You can show this picture with fewer pixels. So what I'm going to do, I wish I could get this thing to brighten up. It looks really dark to me. Does it to you too? Yeah, I can get closer to this thing. Part of the problem is my glasses are like kicking in. So what I'm going to do is grab this image, and we're going to go to Photoshop. And I'm going to pull Photoshop up. And in the meantime, I'm going to make myself full screen. It's a little scary. Apologize. Should have warned you guys. And I'm going to take a picture of... Oh, I got both of them here at the same time. That's actually awesome. That's what I want. So I'm going to open this file up. Okay, that's this one. That's fine. And what I want to show you is what this looks like, but in order to do it, wrong. There. I'll zoom in on what this looks like, but I will do so immediately after the break. We will be right back.